Yes. All right. So we just the MMath entrance exam took place, the 2022 MMath exam, maybe a few hours back. Yeah, it's got over. MMath, this is ISI MMath. Yeah, and maybe I would just like to quickly discuss the subjective questions. Okay, because I have the questions with me. So not just this, not it won't really be a big discussion, but I would just try to say the solutions as much as I have got them, and then we can see. Okay, so I can just say subjective solutions. Just let me call it solutions. Obviously, not full detailed solutions, but just the ideas maybe solutions of subjective portion. Okay, and if I get the time, maybe I can also try to. I have myself have not solved all of them, but maybe the MCQ questions, but maybe tomorrow or after some time. Okay, but subjective questions I feel are more interesting. Okay, so let's subjective portion. Let's discuss them. Exciting because the exam just took place a few hours back. So these questions. So first of all, is the pattern very different this year? No, it seems like this is standard. There's a standard one problem about asymptotes that is there, problem number one, as in the thing I have. And then there are some questions on rank. And in fact, there are two questions which are very similar on projections. And yeah, some ring theory, then two uniform convergence type of questions. And yeah, and one like pseudo functional analysis type of question, just kind of thing. Let's begin with question number one. So maybe I will write the questions, but not in complete detail. Okay, because so that the question is there right in front of, because maybe it's not accessible right now. All is not accessible in one place. Maybe it's there, some of it is there on UPS, and here and there you can find. But for those who have not written the entrance, it's not accessible. So I'll just write the questions in short. Okay. So the first question essentially is saying that you have a real differentiable function. Okay. A real differentiable function, and even let me just say f dashed is continuous. So this just says that it also exists, continuous, and you are told that. So as I said, this will not really be a detailed discussion with related questions, but just quick solutions maybe. Okay, that's just a utility of it. And so this is just saying that it has an asymptote, and we also have f dash x. I mean, the limit of this is 0. Now already you can sense that this b should be 0 maybe. But that's what the question is asking. Okay, show b is equal to 0. But remember that it is important that f dashed is continuous. Okay, so this is a rather standard trick type of question. So let me say maybe the solution. You should, especially if you have not tried, you should pause and try the problem. That's the real utility. But yeah, the solution can be, so we know this, and the way maybe is that you just know that this limit exists. Yeah, I mean, limit of this exists because that's what's given. Yeah, it's equal to a. Okay. Let us now differentiate the new. Now we know that this is equal to limit of x tends to infinity e to the power x fx plus f dashed x by e to the power x. Just differentiating the numerator and denominator. That is the L'Hopital's rule. But there is a slight catch here. Okay, you have to say why this exists. Okay, existence of the limit doesn't imply the existence of this thing. So you have to say why this exists. So you have to explain why this limit exists. Okay, but you see, this is equal to, so color has changed. This is equal to limit fx plus f dashed x, which exists. Yeah, this exists. It is important that this exists independently. Okay, so since this exists, so then by L'Hopital's rule, this limit and this limit, they are all equal. Yeah, and then it's trivial because this is a plus b. Yeah, this exists because f dash and f, both the limits exist, and this is a, so b is 0. So in that sense, it's a simple question. But if you try to use the definitions of limits and try to do, that is what I tried first, and I got a little stuck because there is a little bit of a thing that comes. So yeah, so I don't know. So just check this and obviously let me know if this is not accurate, because all this has been done in a haste just to get the solutions quickly on the table so that we can use it. So that's the solution. Then let's move to the next. Maybe I just can keep this here and let's go to the next one. All right, let's move to problem 2. So this is the standard linear algebra question. In fact, as I just observed now, problem 2 and 3, and one can even say on some level 2, 3, and 4 are all on the same theme of projections. Okay, but maybe we won't go into this abstract thing, but at least that with that I knew that I can do these things easily with having that thing in mind. So maybe we can discuss that kind of thing later sometime. So here we have transformation, linear transformation, finite dimensional, and it's an interesting map. The map has this property that yeah, so it's a similar question where the rank is the same. The rank does not decrease. The rank will a priori it doesn't increase, but it may decrease. But here the rank doesn't decrease. Okay. So yeah, this is what the question is, and what we want to show is that the kernel also does not increase. Yeah, so we just want to show that the kernel of t is equal to kernel of t square, but this is just follows from rank nullity, right? If the rank does not decrease, then the kernel does not increase because the sum is a constant. Yeah, so just maybe I'll just say rk rank of t plus kernel of t is n, but then the domain kind of is the same. The domain is the same, so this is also rank of t square and kernel of t square. So from here you can just see everything is okay. And so this is simple once you use the rank nullity theorem. That's the only theorem really if you want to do it like that. Obviously, one can try to do this more creatively using matrices and such, row rank, column rank, and so on. But that's the same thing eventually. Yeah. The next question is that, and that's really interesting, is that the kernel, so the kernel, which is a subspace of V, but then you think about it, the image, so they call it T of V, they can just say image, T of V. T of V is also subspace of V because the map is from V to V, same vector space, not just under representation, same coordinates, but the same vector space. So, and we want to say that, and that's important because we are taking intersections, a set theoretic intersection, and we want to say that it is empty. And this is really a fundamental thing. This is basically maybe then saying, as I see it, is that then V becomes a direct sum of these two spaces. Okay, direct sum in an interesting way, right? Because T invariant direct sum, I think. So they become KT submodules, but but we don't need all that. I mean, this is just something that, well, I mean, just so if V, so which is the way we should do. So, I mean, just if V, let's just not say V, if let's say TV. So if there is a TV which is in the kernel of T, so one has to just try like this, a kernel of T, then what happens? Yeah, then what does this mean? It means that, so let's say that TV is not equal to 0 and it's in the kernel, which means that T square V is equal to 0, right? So T of V is not equal to 0, so this is the element in the image and it's also in the kernel. So if that is the case, yeah, then in that case what happens? Let's see. So then we are seeing that basically that there is this point, and T of V is not 0, which means that V, so that is basically implying that V is not in the kernel of T. That's what it's saying. But then V is in the kernel of T square, which means that the kernel has grown, right? Which means that the kernel has grown. I mean, you always know that the kernel of T will be a subset, may be equal to kernel of T square. This is always true, right? You can check that. But then here we are getting that the kernel has grown, so we are getting this. But that's the contradiction to part A. So we are done, right? So rather simple, this question, right? So that's what the question 2 is. And now let's move to question 3. Quick, we are trying to go quickly. So just to come back here, I mean, this, yeah, so this does say that, 1 minute. So as the solution is done, but kernel of T directs some TV directs in the image, that is the whole space. That's what it's saying. But then as I see, the question 3 is the same. In that sense, it's very, very same. Not to say anything in that way, but it looks very same to me on one level. Okay. So what is it? It's just a bunch of conditions. So this P1 and P2 are again, now we had one map earlier, now we have two maps. Okay. And basically together, P1 and P2 give you the whole space, and they are kind of orthogonal to each other in the sense that this is 0. So not in the sense that they commute, but the main thing is that their composition is 0. So you go by one, and then when you go by the other, it's 0. That's really the key in splitting a space in that way. But some very simple checks that they are asking us to do is to basically show that indeed these are projections, and they're even calling them P, but these are really projections. Okay, now you can see the similarity of this with the previous question. It's very, very similar in that. Okay, so this is very simple to prove, but really what this is saying is that, I mean, that there is a part of V, which you are, I mean, I should not say a part of V like that, but maybe this is V, and you're kind of mapping V to a subspace of V, okay, subspace. And then this subspace is really going to itself. So on this subspace W, maybe that's the image of P, right? It's the identity. That's what they're asking us to prove. Okay, and what that really does is we can show then that there is a complement which really goes to 0. Okay, that complement is really going to go to 0, and that is the kernel. Yeah, I mean, yeah, that's the kernel, and this is the image, and they don't intersect. And that's really the last part which they in the end asked you to prove. And that really says that it's a direct sum splitting. So the previous question is also that same thing. Yeah, if you look at it, 2 part B and 3 part C is also similar. We'll come to it. This is very simple to check. You just take any V, and so you do it for P1. So you do, you take V, you take P1V. Now you take P, you can take P square, but you can just the way they have set it up, you can write it as 1 minus P2, and then you know P1, P2 is 0, so this really just becomes P1B. And similarly, so this is really simple. So let's just keep this condition. We have proved it, and then it's very simple. I mean, now the thing is that if V is in the image, if something is in the image, then what they're asking us to show, if something is in the image, then that point does not really move. Okay, so if this is the case, then we want to show that, so let's see. So if there is P1W, that then it is V. What we want to show in the end is that P1 of V is V. That there is a part of the space that it did not move, and you projected everything to that part. That is what the whole thing is. Okay, so this, and now this should not be difficult, because you just take, I don't know, you take P square, and you take P1, and this is P1V, P1W, but this is just V. So there you go. That, so anything in the image does not move. That's it. And it's very simple, right? So then that's the thing. And then we just want to then in the end show is that the image of P1 and the image of P2, they have nothing in common. Yeah. Well, the P2 is really the complement map. Okay, so it's a projection, and P2 of V, the image of P2 is really the kernel of P1, is really what it all is. And then, but we can just check this. So I mean, if there is a W which is in P1 V1 and it is equal to, so this is equal to P1 V1 and this is equal to P2 V2. So then, I mean, again, you can just take some, like this. So what do you get? You get P2W is equal to 0. And similarly, you get that P1W is 0. So if P1W and P2W are 0, then W better be 0 because of this condition. W has to be 0. So W0 is the only intersection. So it's a rather simple question. Once again, it's simple. Let's move to the next. So you see both these questions, if you go back to this question and if you look at this question, these two are really this very similar questions. Maps which are projections. Yeah, anything which is like an idempotent. Yeah, in the sense that pi square is equal to pi, p square is equal to pe square, whatever notation you use, right? Anything that is an idempotent, when you take consider it as a map, when you consider it as a homomorphism, endomorphism, whatever, right? Then it just its image is really something which does not move. So in that sense, the image does not move, and so the image and the kernel, they don't intersect. That is really what we have been proving, this and that. And that basically means that it leads to a splitting of the vector space. But it's not any ordinary splitting. Yeah, the point of the splitting is that these subspaces that you get, yeah, I mean, P1V and P2V, right? These two subspaces. I mean, these two subspaces are in P1 invariant. That is the point. Yeah. So yeah, I mean, at least yes. So that's really the thing. Yeah, and basically these direct sum decompositions, when they are later on, we try to generalize them to other places. This is the things that we build on and we do it. Okay. Yeah. And now question 4 is also similar, but it's just for groups. Okay. So you can understand these questions were made by maybe the same person and just similar variations and different disguises, and it's there. So yeah, the question number 4 is, so H is so this is a normal subgroup of G, and now you can just see, right? So we have this G and H is a subgroup. And now what they're telling you in the question is that there is really a map pi from G to H. Okay, and this is a surjective map. And what is the property of this map is that, so we are not, the whole map is not told to us, but I think what's said is that pi of H is H. So H goes to H. So again, you can see, right? So the image is H and that portion is going to itself. Similar to the previous questions. Obviously, question number 2 is not exactly the same. It maybe it's an isomorphic copy or whatever, but 3 is exactly like this, but it's just a different place. It's vector specific, but it's just a non-commutative version of that in some sense. But trying to solve this is what it is. And now we are trying to say is that G is, I think a lot of wrong proofs of this can be easily given. But please check if my solution might also be with C, can also be wrong. So you should just check it. Now, this is the map. Now, basically, if you want to split the G, that is the point, right? I think the simplest way to do this is we just consider the kernel of this, kernel of pi. Let's see, and you take this inclusion, and this is obviously injective. Well, you can forget these arrows if you're not, if you don't need to know what that means. The point is, pi is surjective. By the very definition, pi becomes surjective, and I is injective. Those two are just to put that in a language, but one doesn't need to bother about it. Okay, now one thing can be seen directly is that G, I mean, at least one thing should be clear is that, so this is what we need to show. So yeah, but one thing is clear, that this G becomes a direct sum of this and H. So why is that the case? Well, I think the reason that, I mean, just having a surjective map doesn't mean that, but in this case, the kernel sits inside G, that's okay. And this is, I mean, this is obviously also sitting inside G, right? And now you see, there's a very beautiful thing happening, right? There is this, or maybe let me call this J, right? There is a J which is going in G, and this composed with pi is the identity. So it's taking a section of G, right? You're taking H and you're putting it inside G. Yeah, and but then you're also able to project it back. That is what becoming a direct summand really means. Okay, that is what becoming a direct summand really means. You can use these things to show this isomorphism quite easily. It's a general fact that this is now an isomorphism. I mean, the second one, the first one we have to still prove. Okay, one can give a very quick proof, but I'm saying that the first, rigorously speaking, I believe we have only proved the second one. Okay, and again, the way you can just do is, well, you know that any G, you can write it as something in the kernel and something in H. I mean, that should be clear, right? I mean, because you take an image, I mean, you take something in H, now that's an image of something. And then that something and that image, they have the same image, and then you take the difference that's in the kernel. You can always write it. That's not a problem. But the fact that there is no intersection is what you need to show. And that really follows from this thing, that there is no intersection. So just check it. Okay. So, okay, now that we have this, how do we get G mod H? We don't have G mod H yet, right? But that's very simple, because now you can quotient by H, and I think now you can say from, okay, so let's not say it in the same line. If we quotient by H, so this is, I believe, the right way to do it. There can be but some other way, but this can be kernel of pi. So is this the right way to say this? I say this is okay, right? Because a direct sum, so when you quotient it out, you get kernel pi. This is fine, because you can just prove this by first isomorphism theorem. Just take the kernel pi plus H and take the projection. Now you can, it's just a direct summand, so you can take the projection, because now it's straightforward. But there are other ways. I mean, so you shouldn't be saying things like, so basically I'm trying to say is that A mod B isomorphic to C, then that means A mod C isomorphic to B. Don't say things like this. Then these are not correct in general. Okay, but this is, when you already have a direct sum decomposition, then it's correct. So then you are done, right? So this G mod H is really the kernel. And so you can take the isomorphism from kernel pi to G mod H, and you can use that to, from this isomorphism, get to the first one. So we are done. You can see the similarity. The point I'm trying to say is that there is a similarity between these things. Okay. All right. So the second question, the fifth question, sorry, in my thing, is really just finding primes in ZX. What are the prime ideals? What are the maximal ideals and prime ideals in ring of integers? So basically, we have what we really have is x squared plus 5. Now I will assume that you know this. You can easily prove this. You can just take substitution at root 5 and can take the kernel x square and send first isomorphism theorem, so on. This is, yeah, what it is. Now, the first question is really the question. Show that any maximal ideal of this contains a prime. So show any maximal, one second. Okay. Maximal ideal of ZX mod this contains a prime. Okay, really what you want is a maximal ideal containing x square plus 5. Okay, so well, that's so because we are basically interested in a maximal ideal of this, which and we're interested in its relation with the integers, right? And so it's just that's the natural idea from that comes from there is to consider this inclusion, which is also obviously a ring homomorphism. But then it's very interesting because let's call this I. Now, if there is a maximal ideal here, and maybe just some abuse of notation, but I'm just going to this thing. Now, that's it. Now you see, if this is maximal, it doesn't obviously mean that the inverse image is maximal. But because this is maximal, we know this is prime. Yeah, follow that, right? If it's maximal, then it is prime. But obviously, we know that the inverse image of prime is prime. So this is prime. So it means that this is either 0. 0 is also a prime, right? In integers, in the ring theory definition, it is possibility. And well, that translates to saying that M doesn't have any elements from the integers, which is possible. Yeah, just take X. That's a maximal ideal, and it doesn't have any. Wait. Huh. Yes, X is obviously no, X is not a maximal. Wait, what happened? Sorry. So anyways, let's keep moving. That's not needed now. So this thing, and now when we have this thing, then this thing basically means it's some prime P. But then you see, if just cutting it short a little bit, if this is the case, yeah, this really means that M. So this would mean that M does not have any integers, right? So this would mean that M intersection Z is equal to 0. Yeah, but such a prime is can obviously primes. You can have primes like this. Prime ideals. Obviously, you could have X. It's obviously a prime ideal, right? Which doesn't intersect with integers, but it cannot be maximal. It's easy to show that this cannot be maximal. You can just say I'll just add 2. I'll put 2 in the generating set, add a 2 or add some non 1 number. It will not be so it's not, and you will still not get the whole ring. So it's not maximal. So this cannot be maximal, not possible. And then you're done. The only other possibility is that it should have a prime. So maximal ideals, but it is coming from primes because prime ideals have this nice properties, not maximal ideals. And so using them, you can show that now I square, I mean this, sorry, the inverse image should have prime in it. And so that means that should have, and then you're done basically. Yeah. And part 2 is really simple because now the moment it has a prime, so you're looking at this thing, or maybe you're just looking at, yeah, now if this has a prime, which you're also quotienting by, they're saying that if you quotient by a maximal ideal, then there are only finitely many things. But when you're quotienting by a maximal ideal which contains a prime, then this basically becomes ZP, right? And this means that when you write anything like this, then the A and the B will just be red mod P, and so the at most P square elements. Right? And so that's simple. Right? Question 6, I believe, was more interesting. At least maybe I did it in a bad way, maybe. It's a very beautiful ideas, I think, and we'll see if this is okay. So it is really first thing that is there is that these are continuous functions. So we have F1, F2, and so on. These are all continuous. Yeah. And R to R, okay. But then there is a very curious recurrence that sort of is given, okay. And also we are allowed to assume, so you can assume this, that assume that Fn uniformly converges to F, okay. Show F is a constant, and then there is some hint, but I don't know if my solution used that hint. So I'll see if I'll try to say first, and then I'll form my thoughts, and then we'll see. Show that F is a constant, okay. So we want to show that f is a constant function. Basically, all the things we want to show that the image of f, everything is just the same. So there is only one point in the image. So what we really, the way I see it is that basically you just take two arbitrary points, x0 and x1. Okay. And what you really want to show is that if you take it, just a second, sorry. That if you take that sequence along x0, yeah, and this converges to L1, you can assume that it converges to somewhere. That's not a problem because that's given to you. It's given, in fact, that it uniformly converges to F. And if you write it along some other point, right, you want to show that these two limits are the same. Yeah, and this is the interesting question. These two limits are the same. So I don't know, how do you understand this? So really, if one should just take examples. Yeah. If you look at, in a sense that one should take the first few n's and see what really it means. See, the first one, it's really simple. It, in the sense that f1 is obviously not a constant function a priori, but f1 has this periodicity. So it is a little, repetitiveness is there. But then if you look at f2, and this is really the iteration of the question, iteration of the condition that we are doing, that leads us to say even more. Yeah, it's leading us to say even more repetitions, even a smaller periodicity or even more repetitions, and like this, right? You see what's happening. So it's kind of becoming more, and I'm not drawing pictures and all now, just because you want to do this quickly, just have it all in one place in a small time. The point is that really the function is becoming same quite often. So it's becoming more and more constant. This is the idea as I see it. Right? But now we can exploit this. Yeah, we can exploit this thing. The fact that the functions are becoming more and more constant. And what we want to say is that eventually the behavior at x0 and x1 is same. Yeah, for eventually means after a certain point, the functions behave similar on x0 and x1. Okay, so the point is that if you go far down, then x0 and x1, you can approximate them by this 1 by n's, right? So what I'm trying to say here is, so I'll need a more space here. So I'll just make this smaller. What I'm trying to say, sorry. Yeah, let's just make it small and keep it here. What I'm just trying to say here is, these, this is what I'm trying to say, that if x0 and x1 are at a distance, some finite distance, we don't really know anything about it. But if you're willing to go down enough in the sequence, then this x0, so let's assume that, x1 is bigger than x0, then this x0 plus m by n, from there you can get almost x1, maybe up to an error of epsilon, right? And you see, for any epsilon, you can find such a n, right? Because you're making jumps of 1 by n, right? So, and how are you going to use it? You're going to use this for fn, right? So this really means that you can take your you can, so if epsilon is small enough for fn, then it means that this thing minus this thing is less than epsilon, right? So basically you start with an epsilon, right? And then you get a delta, which you need for this to happen. And then for that delta, you pick a n, large enough, right? If you pick the n, so So wait, so you want the image, so you want, so this fn, so that now is looking at one function fn. So x1 is a point, and you want to go, so you want to find a delta neighborhood. So you want to keep it in the epsilon neighborhood, the images. So then you take a delta neighborhood for that. So yeah, so you would want to make sure that this is less than delta. Yeah, so that's a slight blunder, right? So you should keep this as delta, not as epsilon, right? So you keep this distance less than delta, then you can manage to keep this functional value less than epsilon, obviously. And for that, you can obviously choose a large enough n, right? But then the problem is that now the n that you have chosen is maybe bigger than this fn. And then, so then you basically just, so then that's the problem. So you see, that's where I am stuck in this thing, to be honest. Yeah. So let's what we really want. See, basically my idea was that I had this fn of x naught, right? This is what I wanted. I mean, this is not, it has to be true. This is certainly true. I mean, in the sense that this is certainly true because that's what we'll be proving in the end, right? That this is true. So this is what I wanted. So for this, you go. So this is what I want for a large enough n. Yeah. So you don't put any condition on n. Yeah, you don't put any. You don't put any condition on n, and you take a. But then if you don't, so if you have an epsilon, so maybe some more deeper things might be needed. I don't know. Yeah. Okay, no issues. So this problem. So if I draw a picture, if I take this x1, right, and I want to find the x naught, and I want to find the n, so that this becomes less than epsilon, right? So if this becomes less than epsilon, equicontinuous, are we going to use equicontinuous? So 1 minute. So there is this x1, and then so if you start with x1 and x naught, and you want fn, you want n so that this becomes as an epsilon. So you start with an epsilon. Okay, start with an epsilon. Now, to find the delta, you need an n, right? So you maybe take some arbitrary n. Yeah, so yeah, that's the problem. Yeah, so if you take some n, fix some n, and then you take a delta, but then for that delta, you may need a larger n, right? So if one has to be really say this honestly, we start with this epsilon, right? And we want this, right? And so you want, so you want this minus this to be less than epsilon. So if you fix a n, right, then you will need a delta, right? And the delta comes that you need to produce. And then for this delta, you need some n. So but that will be some n1. So that's not the same n. So now let's think, if that n1 is larger than this n that I started with, yeah, then can I then say that f of n1 x naught by this minus f of n1 x1 is less than epsilon? Yeah. So, right. I mean, if the n is lesser, there is no problem. You can always make it bigger, that you can check, right? You can always just multiply, divide, make it. That's not a problem. You get better, finer divisions, bigger. But now when you take a larger n1, then does it? Yeah. And so for this, I think we have to use the Cauchy convergence. So this should not be difficult. So this is not difficult at all because, well, you know that again for this epsilon, now you can pick another large enough something, some n naught, so that what I'm trying to say is that fn x minus fm x is less than epsilon. So the point is that this fn and fm are close, are close to each other. And so using that, you can show that this difference minus this difference will be less. Now it will not be epsilon, maybe 3. You might need epsilon by 2 here, but yes, you can guarantee this. But basically, given this epsilon, you have to go to that epsilon by 2, find a large n for that, and then take the larger of all of them and kind of there everything there will work out. Okay. So we can kind of say this. So so you can say this because you can take the n to be n1, right? So you can say this, and then so then basically this is good. So in the end, the point is that we can say this. Yeah, we can say this, right? And then you see, I'll just maybe say it diagrammatically. You have the, so I mean you have the m and you have the n and you have x naught, x1, x1. Right. What you want to say is that this gap, you want to make it small because you have shown that this gap is small, right? You obviously, but you know that this gap is obviously can be made small because FIs are uniformly convergent. So FN and FM at a particular point, they will be close to each other. And this also. And so this will be less than 3 epsilon at most. You can see that, show it, and then you're done, because then for all, and this will really work for all m, you see, it doesn't really depend on itself. When the m changes, it's not going to matter, provided you have this Cauchy criteria that says that that this gap is less than epsilon, no matter what the m is. So yeah, so you start with 1, you show the gap is small enough, and then you use the fact that all the at fixed points, the terms are, the function, the sequence is closer and closer. And so then, it's the quadrilateral, so the fourth side will also be. So that is mostly what this is, I think. Okay. So if I've said wrong things, please tell me. The next question, I was first doing this by a really big, stupid way. In a sense, I was using some stone Weierstrass and so on, but it's not really needed. So, well, the question first is that this one is really something that I did. So I didn't feel the question clearly. So this is continuous. And then there is this part A. is this thing, and we want to. So first I was a little, a little shocked at the statement. So maybe that's why I thought that it must be a hard, must need more technology. So there is n plus 1 n fx dx. So I first tried by Stone vs Truss. Let me not go into the details. And I got something, but then it felt really fishy that I did not really use that epsilon approximation of this by a polynomial. I kind of saw that any epsilon works. And so really, then that really means that any fixed epsilon, but then that really meant to me that all you need is the fact that it is bounded. And it is clearly given that it's on a closed interval. So, but I thought, okay, closed interval means Stone vs Truss works on a closed interval, but really you don't need. So you just need this, but just work it out that when you multiply by x to the power m and n plus 1 and so on, and then you do the calculations. Now this really works. So you can, this side also is that you can work it out, but when you do the integration, array, and you will need the fact that a is less than 1, because eventually I think you'll have something like this. And so a is less than 1 is needed to say that that limit is 0. I mean, on the two ends, and then sandwich, you can say. And really at the end point, it's just the second part is that if f of 1 is, how do you extend this result at a equal to 1 when f of 1 is 0? But this is really simple, because it's just a standard thing that what you do with integrals. So you collect at 1, you again, make it small. You make the effect of it small. So basically function like this, right? So you can just find a delta so that in this neighborhood, it's just in this epsilon neighborhood, right? So all I'm trying to say is that from delta to 1, fx x to the n plus 1, this you can, so you can make sure this fx is less than epsilon, right? So this becomes this, and now you can do from delta to 1, and similarly you can do this side. Now you have to work these things out, delta to 1, and when you do this calculations, so what do you get? Yeah, so then you will get something like a delta to the n or something like that. But then delta is less than 1, so the limit, in the limit, it really goes to 0. And that you will need that, right? You need to show that the limit is 0. And f of 1 equal to 0, then also you want to say this, but for this, that's the question, sorry. And then that's it. And then this part you have done, and then from 0 to delta, that is really what we have already done, 0 to a. When a is less than 1, delta is less than 1. So that's pretty not very difficult. The last question is really just a lot of notations, maybe, but it's very, very simple. So do I have time? So yeah, so the last question, let me not do, because I have to rush somewhere. Last question is really simple. Just to write things and just triangle inequality. Triangle inequality